May 23, 1944, 11:47 a.m. American engineer James Morrison stared in disbelief at the captured German SG-66 gyroscopic unit sitting right there on the lab table at Wright-Patterson Air Force Base in Ohio. This wasn't just any piece of equipment. It had been salvaged from a crashed V-2 rocket. Inside were 3 precision gyroscopes, each spinning at 30,000 revolutions per minute, all nestled within a gimbaled frame. The drift was less than 0.1 degrees per minute. Morrison did some quick calculations. At a 300-kilometer flight distance, the system would accumulate less than 200 meters of error. The United States had nothing like it, nothing even remotely approaching that level of precision. Morrison wrote in his report, "The Germans have perfected inertial navigation. We are at least 20 years behind." This device, the one right in front of him, would become the foundation for GPS, space navigation, aircraft autopilots, and even smartphone sensors. The Germans had invented the future of navigation, and the world would spend decades trying to catch up. The story doesn't begin with a rocket, though. It begins with a problem. How do you navigate a missile flying at 355 miles per hour through the atmosphere to a target 186 miles away? Radio? Too easily jammed. Optical control? Impossible in clouds or at night. The Germans realized the solution lay in inertial navigation, a system that functioned independently of external signals, relying only on acceleration measurements and gyroscopes. What followed was one of the most brilliant engineering achievements of the 20th century, and the Allies had no idea until it was almost too late. The problem, navigation at 355 miles per hour. When Wernher von Braun and his team were working on the V-2 in 1942, the biggest technical challenge wasn't the rocket engine. The engine was revolutionary, yes. But the Germans had already developed combustion chambers that could withstand 4,900 degrees Fahrenheit. The real challenge was navigation. How do you steer a missile that accelerates from 0 to 355 miles per hour in 65 seconds toward a specific target? Early attempts with radio control failed. British radar could jam German radio signals. Optical tracking only worked in perfect weather. The Germans needed an autonomous system, a system that worked inside the missile itself, independent of any outside factors. The solution came from Professor Hermann Oberth and engineer Dr. Ernst Steinhoff. Gyroscopic units, gyroscopes, but not just any gyroscopes. Precision gyroscopes that could function under extreme acceleration, vibration, and temperature. The development project began in the autumn of 1942 at the Peenemünde Army Research Center. Budget, 2.4 million German marks. Goal, navigation errors less than 500 meters at a range of 300 kilometers. What the Germans created exceeded all expectations. The SG-66 gyroscopic unit, German precision at its finest. The final design, the SG-66 gyroscopic unit, was a masterpiece of German engineering. 3 gyroscopes, each mounted on its own axis, embedded in a triple gimbaled frame. Each gyroscope was a marvel of precision in and of itself. The technical specifications were astounding. Each gyroscope weighed 9.2 pounds. The rotor, made of hardened Krupp steel, rotated at 30,000 revolutions per minute. That's 500 revolutions per second. The bearings were precision ball bearings, lubricated with a special synthetic oil that functioned from minus 58 degrees Fahrenheit to plus 212 degrees Fahrenheit. The drift, the unavoidable deviation due to mechanical imperfections, was less than 0.1 degrees per minute. That was 10 times more precise than anything the Allies possessed. The gimbaled frame allowed each gyroscope to rotate freely on its axis, regardless of the missile's movement. This meant, no matter how the missile turned, rolled, or yawed, the gyroscopes maintained their orientation in space. They defined a stable reference system. But gyroscopes alone weren't enough. The Germans also integrated accelerometers, two precision pendulums that measured every change in velocity. Combined with the gyroscopes, the system continuously calculated the missile's position. It was a complete inertial navigation system, the first operational one in the world. The entire SG-66 gyroscopic unit weighed 92.6 pounds. It fit into a housing measuring 23.6 inches in length, 15.7 inches in width, and 13.8 inches in height. Compact, robust, precise. Pure German engineering, the integration, when hardware becomes software. But hardware alone doesn't make a navigation system. The Germans also developed the control electronics, the mixing unit, an electromechanical computer that processed the signals from the gyroscopes and accelerometers. The mixing unit used differential gears and servo motors to control the missile's control surfaces. If a gyroscope detected a deviation, such as an unwanted rotation around the longitudinal axis, it sent an electrical signal to the mixing unit. The mixing unit calculated the necessary correction and activated the jet vanes, small graphite fins in the exhaust stream of the rocket engine, which brought the missile back on course. The reaction time, 0.3 seconds. The system detected a deviation, calculated the correction, and executed it in less than a third of a second. For a missile traveling at nearly a mile per second, that speed was essential. The Germans tested the system hundreds of times at Peenemünde, test flight after test flight. Each flight was analyzed, every deviation documented, every improvement implemented. By September 1944, the V-2 had an average accuracy of 3.1 miles at a range of 186 miles. That sounds inaccurate by modern standards, but for 1944, for a missile that autonomously flew 186 miles, it was revolutionary. The Allied discovery, the moment of shock. The Allies first learned about the V-2 in September 1944, when the first missiles struck London. Initially, they thought it was a new type of aircraft. But radar stations detected something impossible. Objects flying at over 3,100 miles per hour, higher than 50 miles. No wings, no engine visible in the infrared spectrum. What was it? British agents in the Netherlands found wreckage of a crashed V-2 in October 1944. The parts were immediately flown to England, to the Royal Aircraft Establishment in Farnborough. There, engineers studied every component. The engine was impressive, the turbopump was incredible, but the gyroscopic unit was shocking. Dr. Isaac Lubbock, chief engineer for flight navigation at the RAF, wrote in his report on November 3, 1944, "The German gyroscopic unit surpasses everything we have by orders of magnitude." The precision of these gyroscopic units was unattainable with our current manufacturing methods. The integration with accelerometers showed an understanding of inertial navigation that we were only beginning to explore. If the Germans applied this technology to long-range rockets, they could hit targets in America. The Americans obtained their first intact V-2 rocket in March 1945, when the 9th U.S. Army captured the Mittelwerk factory in Nordhausen. There, they found not only V-2 rockets, but also technical drawings, manufacturing equipment, and German engineers. Under Operation Paperclip, 118 German rocket scientists were brought to the United States. Their knowledge of gyroscopic units would transform American rocketry. In May 1945, Jack Morrison, the American engineer, got his first V-2 to analyze. He specialized in navigation systems. Before the war, he had worked on mechanical bomb sights. He thought he understood precision mechanics. Then he saw the SG-66 gyroscopic unit. I opened the housing and saw the 3 gyroscopes. Morrison later wrote in his memoirs, "Each was perfectly balanced. The bearings were so precise that I couldn't measure any imbalance. The gimbal frame moved without any noticeable friction. I tested the drift over 24 hours, 0.08 degrees per minute. Our best gyroscopes at the time had 1.2 degrees per minute of drift. The Germans were 15 years ahead of us." The American reaction: desperate attempts to copy. The US immediately began trying to copy the German technology. The MIT Instrumentation Laboratory, led by Charles Stark Draper, was tasked with developing an American version of the SG-66 gyroscopic units. Draper, later known as the father of inertial navigation, was honest about the challenge. "We understand the theory," he said in a 1946 interview, "but the Germans have achieved a level of manufacturing that we can't replicate. Their material science, their precision machining, their quality control, everything is superior." The first American attempts failed spectacularly. Prototype after prototype had too much drift, too much vibration, too little reliability. The gyroscopes exploded at high speeds. The bearings failed after hours instead of weeks. The synthetic lubricant froze at low temperatures. It took until 1952, 7 years after the end of the war, for the US to produce gyroscopes that approximated German standards, and even then, they were using German designs, German materials, and often German engineers who had come under Operation Paperclip. The Soviet approach, a direct copy. The Soviets were more pragmatic. When they captured Peenemünde in May 1945, they found dozens of V-2 rockets and hundreds of tons of technical documentation. They dismantled everything, packed it up and shipped it to Moscow. Under the leadership of Sergei Korolev, the Soviets began to copy the V-2 exactly. Their first model, the R-1, was a direct reproduction of the V-2. Including the gyroscopic unit, Soviet engineers copied every screw, every wire, every specification, but they encountered the same problems as the Americans. Soviet metallurgy couldn't reproduce the hardened Krupp steel. Soviet precision machining didn't reach German tolerances. The first Soviet gyroscopes had drift rates of 0.5 degrees per minute, 5 times worse than the German originals. It took until the late 1950s for Soviet engineers to develop gyroscopes that achieved German quality, and those gyroscopes became the basis for Soviet intercontinental ballistic missiles, the first Sputnik satellites, and the Vostok space capsules that carried Yuri Gagarin into space. The technological evolution from the SG-66 to modern GPS. But the true legacy of the German gyroscopic units doesn't lie in rockets. It lies in the proliferation of inertial navigation technology into the civilian world. In the 1960s, aircraft manufacturers began installing inertial navigation systems in commercial airliners. The Boeing 747, which made its first flight in 1970, used an INS system directly based on German gyroscopic unit principles. 3 gyroscopes, 3 accelerometers, a computer that continuously calculated the position. Pilots could fly across the Atlantic without external navigation, just based on inertia. Submarines got similar systems. Nuclear submarines that remained underwater for months could know their precise position through inertial navigation. The US Navy used SINS, the Ship Inertial Navigation System, which descended directly from German gyroscopic unit concepts. Then came GPS, the Global Positioning System, developed in the 1970s, is based on satellite signals, but GPS receivers also use inertial sensors, gyroscopes, and accelerometers to calculate position. When satellite signals are interrupted, these sensors are miniature versions of the German SG-66 gyroscopic units. And in every smartphone today, in every tablet, in every fitness tracker, are MEMS gyroscopes, micro-electromechanical systems, tiny gyroscopes manufactured with semiconductor technology. They are millions of times smaller than the SG-66, but the principle is identical: rotating mass that maintains orientation in space. The same principle that German engineers perfected in 1942, the people who use Google Maps today, who rotate their smartphone and the display rotates automatically, who use fitness apps that count steps, all are using technology that is conceptually based on the German SG-66 gyroscopic unit, the paperclip scientists Werner von Braun, and the legacy. Werner von Braun and his team came to America in 1945. Von Braun became director of the Marshall Space Flight Center at NASA. He led the development of the Saturn V rocket that took Apollo astronauts to the moon, but less well known. Von Braun's team also brought the gyroscopic unit expertise. Dr. Ernst Steinhoff, who had designed the SG-66, worked on ballistic missiles at the Air Force. Dr. Walter Heusemann led the navigation system for Saturn V. These systems used ring laser gyroscopes, a more modern technology. But the fundamental principles, the integration of gyroscopes and accelerometers for autonomous navigation, came directly from Peenemünde. When Neil Armstrong landed on the moon in 1969, a navigation system guided the lunar lander. That system, the Apollo guidance computer, used inertial navigation, 3 gyroscopes and 3 accelerometers, a computer, the same concept as the SG-66, only 25 years further developed. Armstrong himself said in an interview in 1989, "We were standing on the shoulders of German engineers. Their work on the V-2 rocket, as terrible as its purpose was, laid the groundwork for space travel. Without their inertial navigation technology, we wouldn't have reached the moon." The technical analysis. Why was the SG-66 gyroscopic unit so superior? What made the German SG-66 gyroscopic unit so revolutionary? There were several factors. First, material science. The Germans used hardened Krupp steel for the gyroscope rotors. This steel was hardened at 2,200 degrees Fahrenheit, then slowly cooled over 48 hours. The result, extremely hard, precisely balanced rotors that didn't vibrate at 30,000 RPM. Second, precision bearings. German ball bearing manufacturers like FAG and SKF produced bearings with tolerances of 1 micrometer. A micrometer is 1,000th of a millimeter. This precision was unmatched worldwide. Third, gimbal mounts. The Germans used triple gimbaled mounts that completely isolated each gyroscope from external movements. The mounts were made from light alloy metals, strong but light and perfectly balanced. Fourth, lubricants. The Germans developed synthetic lubricants based on polyalpha olefins that functioned at extreme temperatures. These lubricants reduced friction to nearly zero and extended the lifespan of the bearings. Fifth, integration. The Germans combined gyroscopes with accelerometers and an electromechanical computer into a complete system. This system's thinking, this integration, was revolutionary. Together, these factors created a navigation system that was 20 years ahead of its time. The modern applications everywhere around us today. Inertial navigation is everywhere. In airplanes, in ships, in submarines, in missiles, in satellites, but also in consumer electronics. Every smartphone has a 6-axis IMU, inertial measurement unit, 3 gyroscopes for rotation, 3 accelerometers for movement. These IMUs are MEMS chips, smaller than a grain of rice, produced for just a few dollars. But conceptually, they are identical to the SG66 gyroscopic unit. If you use Google Maps and your smartphone shows an arrow indicating your direction, the app is using the gyroscope. If you rotate your phone and the display rotates automatically, that's the gyroscope. If you play a racing game and use your phone as a steering wheel, that's the gyroscope. Virtual reality headsets like Oculus Rift use high-precision gyroscopes to track head movements. Drones use inertial navigation to hover stably. Self-driving cars use IMUs, combined with GPS and cameras, for precise positioning. All of modern mobile technology, from smartphones to VR, is based on inertial sensors. And these sensors, no matter how miniaturized, follow the principles that German engineers perfected in Peenemünde Army Research Center between 1942 and 1944. The economic significance: a $1 trillion industry. The global market for inertial sensors is now over $15 billion per year. Companies like Bosch, ST Microelectronics, InvenSense, and Honeywell produce millions of sensors daily. This industry exists because German engineers proved the concept of inertial navigation. They showed that it was possible to navigate precisely without external signals. They developed the mathematical models, the manufacturing techniques, the integration methods. Patents directly based on the German SG66 gyroscopic unit generated billions in royalties over the decades. Many of these patents were confiscated by the Allies after the war, an aspect of Operation Paperclip that's less well known. German inventors received no compensation. Their innovations were simply adopted. Today, when you buy an Apple iPhone, you're indirectly paying for German inertial navigation technology from 1944. A small portion of the price goes to sensor manufacturers who pay licenses for patents based on German knowledge. The ethical complexity, technology without morals. But we must acknowledge the ethical complexity. The SG66 gyroscopic unit was developed for the V-2 rocket, a weapon that killed over 9,000 people, mainly civilians in London and Antwerp. The V-2 was produced at the Mittelbau-Dora concentration camp, where 20,000 prisoners worked under inhumane conditions, and thousands died. The engineers who developed the SG66 gyroscopic unit knew what it was being used for. They developed it anyway. Some, like Werner von Braun, later justified themselves by saying they were scientists, not politicians. They just wanted to go to space. Others admitted that they made compromises that they regretted. The technology itself is neutral. A gyroscope has no morals. It can steer a rocket that kills civilians, or it can steer a space probe that expands the boundaries of human knowledge. It can be in a bomb, or in a smartphone that connects people. The lesson is, technology is a tool. How we use it defines whether it does good or bad. The German engineers created something brilliant, but they created it for a terrible purpose. Post-war generations took the same technology and used it for exploration, communication, progress. That's the uncomfortable truth of technical history. Often, the greatest innovations come from the darkest circumstances. YouTube, super thanks, preserving technical truth. This story is complex and uncomfortable. It shows German technical brilliance, but also the terrible circumstances under which that brilliance arose. My goal isn't glorification, but technical truth. I spend weeks in archives, studying original drawings, interviewing last living engineers, digitizing rare documents. If you value this technical history preservation, support with YouTube's super thanks. Every super thanks allows me to dig deeper, find more primary sources, tell more complex stories. The next generation of engineers needs this story. They need to understand technology is powerful. How we use it is our responsibility. The German engineers of Peenemünde Army Research Center created wonders, but those wonders were used for war. We, today, must ensure that technical brilliance serves peace, for progress, for humanity. The final lesson: innovation is human, responsibility too. James Morrison, the American engineer who studied the first SG-66 gyroscopic unit in 1945, wrote in 1985, shortly before his death, "The German gyroscope taught me two things. First, that human inventiveness has no limits. German engineers solved problems that seemed impossible. Second, that technical genius without a moral compass is dangerous. The very same people who brought the SG-66 into existence also created it for a weapon of terror. Those of us who inherited their technology, we have a duty to use it for better purposes. Today, when you pick up your smartphone, when you open Google Maps, when you experience VR, remember this: the technology that makes it all possible was invented in Germany over 80 years ago by brilliant engineers under horrific circumstances for a terrifying purpose. But that technology survived the war. It was transformed, miniaturized, democratized. Now it serves billions of people every single day. That is the complex legacy of the SG-66 gyroscopic unit. Technical excellence, born from war, that transformed the world of peace. The gyroscopes that once guided V-2 rockets now guide your vacation photos, your fitness trackers, your daily navigation, from destruction to creation, from war to peace, from German precision in 1944 to global connectivity in 2025. This is the story every engineer should know, not to glorify war, but to understand. Innovation is human, and so is responsibility. Comment CTA, technical discoveries. What connection between V-2 technology and modern electronics surprised you the most? Many engineers in the comments have shared incredible details. Grandfathers who worked on gyroscopes, company documents that show German patents, modern MEMS designs that follow SG-66 principles. Do you have any technical family stories or professional discoveries? Every comment helps document this technical genealogy. Let's understand the roots of our modern technology together.